Alright, so in a previous video I talked about how cyclic monosaccharides like this green cyclic glucose can react with alcohols like this pink alcohol to form acetals and ketals. And I believe that I mentioned that sometimes the alcohol that comes in and is reduced is actually another carbohydrate. So let me kind of draw this in here. And it makes sense because what you see with carbohydrates is that they're chock full of hydroxyl groups. They're chock full of these OH groups. And so really they can function really similarly to alcohols in reactions. And when this happens, the individual monosaccharides are linked together to make an acetal. And we call this linkage a glycosidic linkage. So this is a glycosidic linkage. Now, when two monosaccharides are linked together in this fashion by glycosidic linkages, we call the product a disaccharide. A disaccharide. And we have di, which means two, and saccharide, which means sugar. So sugar, so two monosaccharides linked together, they're called a disaccharide. Now with disaccharides, most commonly the glycosidic linkage forms between the anomeric carbon or C1. So remember, this is the anomeric carbon. We've got C1. So over in our glycoside here, it'd be right here, just the same. We've got C1 of the first sugar, and then C4 of the second sugar. So right here would be C4. And it's just the same over here. So right here we have C4, and that's the second sugar. So we call this a 1,4 glycosidic linkage. And then just like we could further break down our monosaccharides into alpha and beta based off the orientation of the anomeric hydroxyl group, we can more specifically call the 1,4 linkage an alpha or a beta linkage. Again, based off what is now the orientation of the OR group on the anomeric carbon. So same rules apply. If the group is cis with respect to the sixth carbon, it's beta, and of course if it's trans it would be an alpha linkage. So in this case, our OR group, which the OR group is this whole carbohydrate, is cis with respect to the C6 carbon, so we have a beta 1,4 glycosidic linkage. And if that bit of naming confused you a little bit, I went over that in greater detail in a different video, but what I want to focus on here are some of the common disaccharides. So let me clear some space, let me give us some room. I'm going to go ahead and fade in a drawing that I did a little bit ago to save just a bit of time. And what we have here is a disaccharide. You see two carbohydrates, two monosaccharides linked together, and this one happens to be lactose, which you might be familiar with. So lactose. And lactose happens to be really the principal disaccharide found in milk, and that's actually true for both human milk and for cow milk. And unlike really most disaccharides, lactose isn't really appreciably sweet. It consists of one galactose, so this one right here is galactose, and then one glucose carbohydrate, and they're bound together by a 1,4 glycoside bond, just like we saw before. So we've got the 1 and the 4, and this is a glycoside bond, and this one happens to be in the beta orientation. So lactose is a disaccharide made of galactose and glucose joined together by a beta 1,4 glycoside bond. Now next up we have maltose. So let me write that in here. We've got maltose, and maltose is again a disaccharide, but this time it's made of two individual glucose units. So we've got a glucose right here and we've got a glucose right here, and they're bound together similarly by a 1,4 glycoside. So we've got the 1 carbon right here, that's this one, and we've got the 4 carbon over here. So this is again a 1,4 glycosidic linkage, but as opposed to lactose up here, this one's actually alpha. You can see that this OR group, the second carbohydrate, which is functioning as the OR group, is in the trans position with respect to the first carbohydrate's 6 carbon over here. So this is an alpha 1,4-glycosidic linkage, and it binds together 2 glucose units. So that's maltose, another pretty common disaccharide. And then last but not least, let me pull in here for you sucrose. And sucrose is actually probably the most common disaccharide in all of nature, and you deal with it quite frequently, I'd imagine, because sucrose is the principal disaccharide of table sugar, which comes from sugar cane. So sucrose is actually quite sweet, but it's different, substantially so, from maltose and lactose. And I want to point out a couple of the key differences. So in lactose and maltose, both of these up here, you have 2 pyranoses. Remember, pyranoses are 6-membered carbohydrate rings. I went over that in a previous video, but we have 2 6-membered rings bound together by this glycoside. And in sucrose, that's different. We've got a 6-membered glucose right here. This is glucose bound to a 5-membered or a furanose fructose. So we've got fructose right here. So fructose. And what happens is you have both of the carbohydrates linked together by their anomeric carbons. So right here, we've got 2 anomeric carbons linked together. Now that's different than maltose and lactose. So, for example, right here is the anomeric carbon of both maltose and lactose. It's over here. That's the C4 that's bound. So these are both linked together by their anomeric carbons. And what happens is you have 2 acetals that are formed. So we've got an acetal right there. And remember, an acetal is when a carbon is linked to an OR group over here and an OR group over here. And then you have a second acetal at the fructose's anomeric carbon. And so with maltose and the same thing with lactose, you have hemiacetals that are formed. So you've got an acetal right here, and then you've got a hemiacetal over kind of on the tail, on the second glucose. That's a hemiacetal. And you can look up, and it's the exact same thing for lactose. But what happens here is, remember that with a hemiacetal, you can add on a second OH group to form another acetal. A hemiacetal can be further reduced into an acetal, but once you have an acetal, you can't further reduce it. So that makes sucrose a non-reducing sugar, and then lactose and maltose are both reducing sugars. And so lactose, maltose, and sucrose are probably the 3 most common disaccharides, and they give us a good basis for disaccharides. And then really polysaccharides are just an extension of this thought. So let me clear some space. And for those reducing sugars like maltose and lactose that are left with a hemiacetal group at the end, we can keep adding sugar groups onto the chain. That's kind of this reducing characteristic. They can keep growing, which ends up making more acetal groups, but always leaving a hemiacetal group on the end. So I've kind of pre-drawn in another drawing here. Let me make a little bit more room for it. And that's what I've shown here. I've shown just kind of the addition, a couple additions of extra carbohydrates onto disaccharides. So both of these have 3 carbohydrates, and you could keep going, but that's what makes them polysaccharides. So this first one that I drew in is a polysaccharide called cellulose. And cellulose is found in the cell walls of really nearly all plants, and it gives support and structure to wood and to plant stems, and really cotton is essentially just pure cellulose. But cellulose is a polysaccharide made of repeating glucose units that are joined together by beta 1,4-glycosidic bonds. So all of these are beta 1,4-glycosidic linkages, and really this it forms an unbranched, just kind of straight change, and that's the polysaccharide cellulose. Now down here I have another polysaccharide which is also super common, and this is starch. And you can see that really this is made up of repeating glucose units here. The difference is that these linkages are alpha. Still 1,4. So still 1,4 linkages, but these are alpha units. And really the functional difference here is that as humans, we have the enzyme to break down these alpha 1,4 linkages, and we can use starch, which again is found in a lot of plant products, as a source of energy, because we can break these down into glucose to undergo cellular respiration, but we lack the enzyme to break down the beta 1,4 glycosidic linkages of glucose, so we can't appreciably use cellulose as an energy source. And then one last polysaccharide that I want to show you is really very similar to starch. So I'm going to use the starch as a little basis here. But if you kind of branch off of the starch every once in a while on the C6 carbon, so that's the C6 carbon right here, and you add on another glucose. So I'll stop there. This is another glucose. You can keep going with alpha 1,4 linkages again, and you can form essentially just branches. So this one would go here, and then you could maybe down the line here have another one. And so these are mostly alpha 1,4 linkages. Every once in a while you get an alpha 1,6 linkage thrown in there, which creates some significant branching. And so if it's highly branched, we call it glycogen. And that's a little bit dumbed down of a concept, but essentially that's what glycogen is. It's a major polysaccharide made of alpha 1,4 linkages with that are heavily branched by these alpha 1,6 breaks. But glycogen, its significance for us is principally as a source of storage of energy. So we can build glycogen stores in our body, and it creates a really functional store of glucose, because with all these branches we have a lot of tails of glucose that can be chopped off pretty quickly to get a fast glucose source. So that's probably a good start for polysaccharides as well. We've got cellulose, which is beta 1,4 linkages of glucose in a straight chain. We've got starch, which is essentially kind of a chain of alpha 1,4 linkages of glucose. And then we've got glycogen, which is really similar to starch, except that there are alpha 1,6 linkage breaks in here that enable us to form kind of chains of this polysaccharide.